All right, we're going here. All right, so now we're going to be talking about chapter 9. We're done with chapter 8. I'll just remind you, chapter 8, we're dealing with hypothesis tests, we're dealing with confidence intervals, effect size, and power. In the chapter 7, we were dealing with hypothesis tests using the Z statistic. In chapter 8, when we were doing confidence intervals, we were still using the Z statistic. Now in this chapter, we're going to be learning a new inferential statistic, and I will argue that the inferential statistics that we're going to learn in this chapter are much more likely to be used in an actual psychology experiment or some experiment in science. The issue with the Z statistic, and it's kind of hinted at here, is that with the Z statistic, you can only use it in a situation which doesn't happen very often. Basically, you can use the Z statistic when you know the mean of the population and when you know the standard deviation of the population. But that is very, very rare in just about any field of science, but definitely in psychology. For instance, I've published several papers and I've never used the Z statistic, though every single empirical paper that I've ever published has done a hypothesis test that's either the exact t-test or one very similar to it, the f-test. I've never done a z-test, but done lots of t-tests and f-tests. And once again, the reason why the t-test is valuable is because it's actually a type of test which is more likely to be used. And it has to do with the fact that you can use the t-test even when the population standard deviation is not known. So we don't usually know stuff about the populations in practice because populations are just too darn big usually. And so getting all of the data, getting those population parameters like the mean of the population or the standard deviation of the population, that actually is pretty rare in real life. And so the t-test, what it attempts to do is you notice the numerator of this t statistic is the same as the z statistic that we've been dealing with recently for sample means. The z statistic for sample means, the numerator is identical to the numerator for this t statistic for sample means. So just like the z statistic, the t statistic is trying to kind of gauge how different are these two means. This is a sample mean right here, and this is a population mean right here. How different are these two means? But please notice how the denominator of the t statistic is different. Someone tell me, does anyone remember you see that we have an S right here now. When we were calculating the z statistic, we didn't have an S right here. What did we have instead right here when we were counting the z statistic? Anyone remember?
Standard error.
Yeah, the whole thing was called the standard error. But if you break down this whole thing called the standard error, what was the top part of the standard error? What was the symbol that was right where I'm circling with my mouse?
Standard deviation, maybe?
Yes, the population standard deviation. But you really got to emphasize the population. Does anyone remember the name of the Greek symbol that we were using? Sigma was the symbol that we were using for population standard deviation. So we're replacing in this equation, we're no longer using the population standard deviation. You can see right here, we don't know you use the t statistic when you don't know the population standard deviation. So instead you use this thing S. And what this S is the sample standard deviation. And I have the equation right here. You've seen this equation. You've calculated you've made calculations using the population standard deviation equation, which are identical to this equation right here. But someone remind me, this is old school thing that we've talked about. How is the sample standard deviation equation different than the population standard deviation equation? Anyone remember what is the primary difference between the population and sample equations for standard deviation?
For the sample, the denominator is n-1.
Thank you. Excellent. Yes, the denominator is n-1. And the reason we do this, the reason why we make the denominator n-1 is because we're kind of penalizing ourselves. Basically, what we're trying to do, we're using S right here instead of the population standard deviation. So we're going to use the standard deviation of a sample. So usually populations are really big, but we're going to, so we're going to take a sample though, which means the subset of the population, and we're going to use the standard deviation of that sample, and we're going to basically assume that the standard deviation of that sample is the same as the standard deviation of the population. However, that's not exactly a safe bet. And so the typical thing to do is to kind of penalize our standard deviation calculation by, instead of just dividing by n, which is what we would normally do with the population equation, for the sample equation, we're dividing by n minus 1, which basically what this does is if you subtract 1 from the denominator, basically what it does is it makes the denominator smaller. And so when you're dividing by a smaller number, the net change is to make the overall standard deviation slightly bigger. So that's why we do this. The standard deviation is slightly bigger, which influences the standard error. It basically makes the overall standard error bigger. This whole thing is going to be slightly bigger if we have an n minus 1 of the denominator of s, because it will make s bigger, which makes the overall standard error bigger, which makes the overall t ratio. Will someone tell me, as you make the standard error bigger, if you make this whole thing right here bigger, what does it do to the overall t ratio? As the denominator gets bigger, what happens to the overall ratio?
Gets smaller.
Yes, it gets smaller. So that is the reason why we have this correction for of n minus 1. When we're calculating the t statistic, we don't know the population standard deviation. Instead, we use the sample standard deviation, which is just the subset of the population. And we assume, okay, this is going to be the standard deviation of our sample will be the same as the standard deviation of our population, but we're not 100% sure that that's true. So what we're going to do is we're going to penalize ourselves, do this n minus 1 thing. Basically what that does is that makes the overall standard deviation bigger, which makes the standard error bigger, which makes the overall t ratio smaller. And if the t ratio is smaller, that decreases the likelihood that t ratio is going to reach those critical regions. Those critical regions are out in the tail. If t is smaller, basically what that means is t is closer to the center of the distribution, is closer to 0, which decreases the likelihood that we're going to find a significant effect. So the whole purpose of this n minus 1 right here is to guard against getting false positives. We change the n minus 1 right here from n, and the bottom line is that changes the t, it makes it smaller, which decreases the likelihood that we will reject the null hypothesis. One thing which I want to point out, which is a little bit weird about the t statistic, is that we don't know the population standard deviation. So we're using s instead, which is sample standard deviation. But if you notice, we still have this population parameter mu right here. So it's a little bit, we still know the population mean according to the t-test, but we don't know the population standard deviation. So this is a little bit weird of a thing. And like, why would you ever know the population mean, but not know the population standard deviation? And there's basically only one situation. I've actually done a couple studies where we've used one sample t-test, and there's basically only one situation in which you would know the population mean, but you would not know the population standard deviation. And that situation is when you can infer the population mean based on probability theory. And I will show you 2 examples in this class. We know the population mean generally with the one sample t-test because we are able to infer the population mean from basic simple probability theory. So kind of unpacking these formulas right here. Now, instead of having the standard error in the denominator of our equation, we now have estimated standard error, which is the exact same thing that we've been dealing with the z statistic, except instead of sigma right here, we have s still divided by the square root of n. So basically the t equation is identical to the z equation that we've been dealing with for sample means, except instead of having standard error in the denominator with sigma, we have estimated standard error in the denominator with s. Let's see, what do we want to talk about here? This is a good summary thing, but I've said some of this stuff. Yeah, okay, so I guess we should talk about the distribution of means for t relative to z. So we've always been dealing with a single distribution of means for Z, but T has many distributions of means. And the reason why we have many different distributions of means for T is because of this idea of a degree of freedom. Each different T distribution is influenced by the sample size. And you should probably write this down. We know it says it right here. Basically, the degrees of freedom that we're going to be dealing with are n minus 1. N minus 1 means whatever the sample size is, we're going to subtract 1 from the sample size. So we have a population with some unknown amount of people. We randomly sample 10 people from the population, and we calculate a sample mean. The degree of freedom for that sample mean would be 10 minus 1. Total sample size 10 minus 1, which would be 9. So here's kind of a way of understanding how we have what it means to have multiple distributions. Here is right here the normal distribution. What is meant by normal distribution is this is the Z distribution right here. It's this dotted line. It's the thinnest out of all of these. It is also the tallest out of all of these. The fact that the normal distribution or the Z distribution is the thinnest indicates that the Z distribution has the smallest amount of variability. But you also see these other distributions right here. So this one with the large dotted lines, the degrees of freedom for this T distribution is 20, which means, by the way, if the degrees of freedom for this one is 20, can someone tell me what is the sample size? What is the N? If the degrees of freedom is 20, what is the sample size that was used for this distribution?
21.
Yes, you go in reverse. If the degrees of freedom is 20, then you kind of go in reverse. That means the sample size was 21 because degrees of freedom is in the sample size minus 1. 21 minus 1 equals 20. And you notice when we have that bigger sample size, degree of freedom 20, which indicates the sample size of 21, we have a relatively taller peak than this peak right here, this distribution right here, which is a T distribution with degrees of freedom equals 5, which means the sample size was 6. So basically, the bigger the sample size gets for the T distribution, the taller the distribution gets, and also the more thin it gets. That is, the less variability the distribution has. So this is all very abstract right now. It will become more concrete when we actually do some examples. In the example, so right here, hopefully some of you guys are following along in the slides. The slides are updated on Blackboard. And so we're going to be using a new table in this chapter, and that's going to be the T table, which I've got mine shown right here. I've copied and pasted a T table into a Google Sheet, and so we all should have access to this T table right here. And so you notice how along the left-hand side of the T table, these are degrees of freedom. So this is what I said. When I said each T distribution, there's a different T distribution for each degrees of freedom. That's shown right here. Now, not every single degree of freedom is shown here, but a lot of them. So it goes 1 through 30 right here, and then it skips 40 to 60, 80, 100 to 1,000. So we're not including every single degree of freedom between 1 and 1,000, but these are a lot of the different T distributions, basically, a lot of the different sample sizes, a lot of the different degrees of freedom that can occur given your sample size. So these are the different degrees of freedom right here. And then up here, these are your alpha levels, depending on whether you're assuming a one-tailed test or a two-tailed test. Remember, we talked about mostly we talked about this in chapter 7. We talked about one-tail versus two-tailed tests, and we have talked about alpha levels now a good deal. The punchline of the T table, what you find in the center, once you know your degrees of freedom, that is sample size minus 1, and once you've decided what your alpha level is and whether you're doing a one or two-tailed test, then what you do is you find these numbers in the center. And what these numbers are critical T values. So we've dealt with critical Z values before. The critical Z value, for instance, this is something that I told you to commit to memory. If we're doing a two-tailed test with alpha equals 0.05 and we're doing a Z test, the critical z is plus or minus 1.96. That critical z, 1.96, means that 2.5% of the area is to the right of 1.96, and 2.5% of the area is to the left of negative 1.96. And if you add up those two pieces of area, alpha equals 0.05, or 5%, is what you would get. So we're doing a similar thing here. Once again, for the z distribution, if you have alpha equals 0.05 and you're doing a two-tailed test, the critical z was plus or minus 1.96. Here we have a whole bunch of different critical t's, and we have different critical t's depending on, once again, the degrees of freedom over here, and also the amount of tails and the alpha level that we choose. So we will I'll kind of minimize this right now. We will be dealing with this in more detail in a second. So, oops. Okay, so here is just an example of a potential way of setting up a hypothesis test that we would use for a given t distribution. So here is a t distribution shown when the degrees of freedom is 3, which means, by the way, that we have a sample size of 4. 4 minus 1 gives us this degrees of freedom 3. We choose an alpha of 0.1, which by the way means an alpha of 10%. We get an alpha of 0.1 equals an alpha of 10%. This, by the way, is an alpha level, which basically is very, very rare to find in any scientific field. Usually it's lower than this. Usually it's 0.05 or 5%. But it's a two-tailed test, and we can see that if we add up, there's 5% in this tail, 5% in this tail. We add those two tails together, we get 10%. These numbers right here, negative 2.353 and positive 2.353, these mark the critical T boundary. So this blue shaded area right here, this is a critical region. This blue shaded area here, this is a critical region. And the boundary into that critical region is marked by the critical T, minus 2.353 and positive 2.353. So let's look at the T table and see if these critical T values right here are correct. So our alpha is 0.1. We have a two-tailed test and a degrees of freedom equals 3. I got it. That's a lot of stuff, so I'm going to take a picture just so I don't forget. All right, got that. So let's now look at our T table. All right, here is our T table. So we have degrees of freedom 3 right here. So our example, once again, the example I just showed you, our degrees of freedom was 3. So we're going to be using this row right here. Our alpha, we had a two-tailed test with alpha equals 0.1. So two-tailed, and our alpha was 0.1. So see how this says 0.1 right there? This is the alpha, and it's two tails. We're doing two-tailed hypothesis test. We're choosing an alpha level of 0.1, which means 10%. We scroll down, or we go down until where it intersects with the degrees of freedom we have. And you see right here, the number, which I'm kind of circling with my mouse, is 2.353. That is the critical T value. And you can see 2.353. That is the critical T value, which is on each side. We have a negative T value, which is the left tail, and a positive T value, which is the right tail. In the T distribution for degrees of freedom 3, it is this T value which marks the boundary to the critical region. 5% is to the left of this critical T, and 5% is to the right of this critical T right here. So that is one example. We'll do some more examples to help us find critical T's here in a second. So now we're going to be learning a specific hypothesis test, using the T. So it turns out we're actually going to learn 3 different kind of variations of the T statistic amongst this is chapter 9. Then we'll also have the paired samples T test, which is another one. And then in chapter 10 is the independent samples T test. So we're going to learn 3 different T tests: the one sample T test, the paired samples t-test, and the independent samples t-test. And by the way, I should mention, many of you guys will be doing independent samples t-tests for your group projects. So we're building up to the hypothesis test that many of you guys will be using for your group project. The one sample t-test, that's the one we're going to learn first. That's the one that we're focusing on today. It compares a sample mean, and I kind of mentioned this before. It compares that to another mean, but the number that it's comparing to, I call a hypothetical population mean. And the book just kind of would call it like a population mean, but we're comparing a sample mean. It's a little bit more accurate to call it a hypothetical population mean. Because remember, for the one sample t-test, you look at the denominator of our t equation that I showed you at the beginning of this class. We don't know the population standard deviation. We know we can calculate the sample standard deviation, but we don't know the population standard deviation. And if you don't know the population standard deviation, then usually you're not going to be able to calculate the population mean either. If you don't have information, one aspect about one population parameter, the standard deviation, in real life, you're almost never going to have information about the population mean either. And so in all practical uses, the one sample t-test can only be used when you can infer what the population mean is, and I mentioned this earlier, based on probability theory. And that's why I call it a hypothetical population mean. That mu in our t equation is not one that we get by calculating a mean. That mu is one that we get from inferring it based on basic probability theory. And so we're going to compare a sample mean, m, to a hypothetical population mean, and that hypothetical population mean is inferred from probability theory. So here's an example. So let me describe what's going on here in this example. So this is a type of research that definitely exists if you're a developmental psychologist. The common dependent variable in studies of infants is the amount of time they spend looking at things. And so here's a study where the participants were infants, they were babies, and the infants would come into a laboratory. And remember, with infants, you can't ask them questions. They can't answer verbally, and they're not very good at pressing buttons. So you're just measuring where the infants are looking. In this case, they're giving the infants two things, and those two things are faces. So imagine a computer screen in front of the infant, and one of the faces on that computer screen is attractive, and the other face on that computer screen is not attractive. And the infants are looking at the computer screen for 20 seconds. And depending on where the babies are looking, each unit of time for that 20 seconds, the baby is categorized as either looking at the attractive face or the unattractive face. Whichever face that the infant's eyes are closer to, even if the baby is not looking directly at the attractive face, if it's looking, whichever face it's looking closer to, it's scored as, if it's looking closer to the attractive face, then you say it's looking at the attractive face. Or if its eyes are looking closer to the unattractive face, then you say it's looking at the. It's always looking at one of the two types of faces for the span of the 20 seconds. And our question is, does the baby spend more time looking at one of the faces than would be predicted based on chance performance? And so if there's two things that the baby can be looking at, and it always has to be looking at one of them, and the baby's looking for 20 seconds, on average, if the baby should spend, if the null hypothesis effect that is true, that is, if there's no effect at all, the baby should spend 10 seconds looking at the attractive face and 10 seconds looking at the unattractive face. I'll say that, so you ask here, what would the null hypothesis be and what would the alternative hypothesis be? Remember, the null hypothesis basically says there's no treatment effect. The conditions don't do anything to the dependent variable. That's what the null hypothesis says in words. If we want to be like, I think I have the null hypothesis written in the notes portion. Yeah, I do. The null hypothesis, I'm highlighting it here, would be the amount of time spent looking at the attractive face would be 10 seconds. And I wrote some notes here about how we came up with that. It's probability. Basically, there's two faces, and if the baby is looking equally at both, if there's no treatment effect, if there's no difference in the amount of time that the baby looks at each face, then the baby is going to look at each face half the time. 50% of the time it's going to look at the attractive face, 50% of the time it's going to look at the unattractive face, which leads to the null hypothesis that the amount of time spent looking at the attractive face would be 10 seconds. This is probability. The exact mathematics would be 50% times 20 seconds equals 10 seconds. The null hypothesis is that each baby will spend 10 seconds looking at the attractive face, which means necessarily that the baby will also spend 10 seconds looking at the unattractive face. The alternative hypothesis would be the amount of time spent looking at the attractive face does not equal 10. So I want to point out that the way I've phrased this alternative hypothesis, this research hypothesis, mu attractive does not equal 10, implies that this is a two-tailed test. The two tails are mu attractive for the alternative hypothesis, for the research hypothesis. The two tails, the unpacking what this means right here, mu attractive is greater than 10 or mu attractive is less than 10. Those are the two tails that we're dealing in. In other words, we got one critical region in the right tail, and we have another critical region in the left tail. And if our test statistic, T, lands in either of those two critical regions, one in the left tail or one in the right tail, then we are going to side with the H1. We're going to side with the research hypothesis, the alternative hypothesis. We'll decide that this is correct, that the baby is not looking at the attractive face for 10 seconds. They're looking at it for either significantly longer or significantly less than 10 seconds. And so now we'll actually do some calculations here. I've shown you the null hypothesis. I've shown you the alternative hypothesis. We're going to assume that the sample size is 9. By the way, if our sample size is 9, what will our degree of freedom be?
8.
8, because 9 minus 1 equals 8. Thank you. So we're going to calculate a sample mean. That's what this is. M equals 13. You might want to write this in your notes. This 13 represents the amount of time that the baby spent looking at the attractive face. Whenever we're talking about means for this example, it's always the amount of time that the baby spent looking at the attractive face. And if you look at the null and alternative hypotheses, that's what I did there. I said mu attractive equals 10 was the null hypothesis. Mu attractive does not equal 10 was the research hypothesis. M equals 13. Whoops. M equals 13 is our sample mean. This is the amount of time that those 9 babies actually spent looking at the attractive face. The sum of squares, this is the numerator part of the standard deviation, equals 72. Back in the day, I would have probably made you do this in class, do a calculation just to get some practice with calculating the sample standard deviation. But instead, I'm just going to show you the calculations on the next slide. So I'll just mention then that the sample standard deviation, which I've calculated for you, is 9. So we need to calculate. So let me show you that actually. Yeah, actually that was a typo. The sample standard deviation is 3. But here's the work for that. So 72 was the sum of squares. And right here, this was n minus 1. So this S right here, this is me working out, going all the way back to this formula right here. This formula, right, let me move this. This is the sample standard deviation right here. So right here, this is our sum of squares, which I said was 72. Our n was 9, so n minus 1 equals 8. 72 divided by 8 equals 9. The square root of 9 equals 3. So going back here, 72 is the sum of squares that I just gave you We're dividing by n minus 1, which is 8. 72 divided by 8 equals 9. Then we're taking the square root of 9, which gives you 3. So the sample standard deviation is 3. That 9 that I had in the previous, the typo that I had, I gave you the variance. That was the variance equals 9. But when we take the square root of that 9, we get 3, which is the standard deviation. Now we need to calculate the standard error. And the standard error, going back to the equation I showed you earlier, remember the standard error is S, the sample standard deviation, divided by the square root of n. So here's our standard deviation right here is 3. Standard deviation is 3. And we're dividing by the square root of 9. That 9 is our sample size. So 3 divided by square root of 9, which basically is 3, equals 3 divided by 3 equals 1. So our standard error is 1 for this problem. And then we need to calculate t. It looks like I'm being cut off a little bit on the bottom here of this picture. But this is the number 1 in the denominator. So t equals 13, which is our sample mean. Once again, this is the amount of time the infant spend looking at the attractive face. This is the sample mean based on n equals 9. And then minus 10. This is our hypothetical population mean. Remember, we did not actually collect data on a population mean. This number 10 was calculated based on probability theory. And this is the single most difficult thing for students to understand about the one sample t-test, is that this number right here is not actually collected from data. It is based on probability theory. And once again, for us, we had infants were looking for 20 seconds. There were 2 faces. So if the null hypothesis was true, how much time would they spend looking at the attractive face? That is, if there's no difference in the amount of time they spend looking at the 2 faces, then they should spend 10 seconds looking at the attractive face. This is what this is right here. So sample mean of 13 minus the hypothetical population mean of 10 divided by the estimated standard error, which is 1, which gives us a t-value here of 3. Okay, so we've just calculated our t-value of 3. What we want to know is, are these infants, are these babies in this study, are they looking at the attractive face longer than would be predicted by chance performance? Is there a difference in the amount of time that they're actually looking at the attractive face compared to the null hypothesis? The null hypothesis predicts they should look at each face, including the attractive face, for 10 seconds. We found that they actually looked at the attractive face for 13 seconds. We want to know, is that 13 seconds significantly different than chance performance of 10 seconds? We've calculated our t-statistic, and we found it to be equal to 3. And so now what we need to do is we need to use that t-table that I showed you at the beginning of class, and we need to look up our critical t. And we need to decide, is that t that we calculated 3, is it in the critical region or is it not in the critical region? And so I'm going to show you a couple different examples or a couple different scenarios here. So first, we've calculated the t-statistic, it's 3. And then I'm asking this question, is that t in the critical region if we assume alpha equals 0.05? So we know that our degrees of freedom is 8. And I said at the top, we're doing a two-tailed test. And so for this problem, alpha equals 0.05, which means if we know those 3 pieces of information, then we can look up the critical t's in our t-table. Once again, we need to know the degrees of freedom. We need to know whether it's 1 of 2 tails, and we need to know our alpha level. Once we know all 3 of those things, then we can go to the t-table, we can look up our critical t. So let's do that. We have degrees of freedom 8, 2 tails, alpha equals 0.05. Let's find what the critical t should be. So degrees of freedom equals 8 is right here. We're doing a two-tailed test, which is with 0.05 right here, 0.05. 2 tails, degrees of freedom equals 8. So we look where those intersect, and our critical t is 2.306. 2.306. By the way, I will work this out for you right here. This is the answer. If alpha equals 0.05, degrees of freedom equals 8, and we're doing a two-tailed test, then the critical t is plus or minus 2.306. It's plus or minus because we have 2 tails. We have a positive critical t and we have a negative critical t. So knowing this right here, our critical t is plus or minus 2.306. Are we in the critical region? Is our t value that we calculated 3, is it in the critical region? Can someone help me? Is it in the critical region?
Yes,
Yes, it is. Do you know why? Can you explain how you knew that?
because 3 is bigger than 2.306, therefore it's farther down on the distribution.
Exactly. So 2.306. This is our critical Z. We also have one over here. Negative 2.306. So these are the two critical boundaries. Negative critical T, positive critical T. The actual T that we calculated is right here. That's 3. That's clearly in the shaded region right here. So 3 is greater than 2.306. Therefore, we are in the critical region. Therefore, what do we do with the null hypothesis if we're in the critical region?
Reject.
You reject. We find a significant effect. We reject the null hypothesis. And so what we would say is, yes, the sample mean of 13 is significantly different than the population mean, or the hypothetical population mean, chance performance, which would be 10. So that was for alpha equals 0.05. And this alpha equals 0.05, by the way, I want to remind you, this means that 5% of the total area in the distribution is in the tails. And so when we use 5% as our alpha level, we find that there was a significant difference because T of 3 was greater than our critical T of 2.306. Now let's do another example. Let's pretend that instead of using an alpha of 0.05, the alpha that we used was 0.01. If we use an alpha of 0.01, what that's going to do is that's going to push those critical regions further down into the tails, further away from the middle of the distribution, farther into those tails. Alpha equals 0.01 means that the total amount of area in the tails is 1%. So just a small sliver of the overall distribution now is in those two tails. There'll be a 0.5% in the left tail and 0.5% in the right tail. If our T value, it's still 3, falls into one of those critical regions, then we will reject the null hypothesis. But now that alpha equals 0.01, using this example of alpha equals 0.01, we need to go back to our T table now and find what is the critical T. If alpha equals 0.01 for degrees of freedom equals 8 and doing a two-tail test, what is the critical T? So let's open up our T table here. So degrees of freedom still equals 8 right here. We're using alpha equals 0.01, two tails. So here it says 0.01.
We can't see the T table.
Oh, yes, thank you. Yes. Yes, good. You can see it now, correct? Okay, so degrees of freedom, 8 is right here. Up here, it says 0.01, two tails. So this is alpha equals 0.01. Alpha equals 1% right here, two tails. We find where that intersects with degrees of freedom equals 8. 8 intersects with 0.01, two tails. The number there is 3.355. That is our critical T. Since we're doing a two-tailed test, it's plus or minus 3.355. That marks the critical region. So if we assume that alpha equals 0.01, I'll go back to this thing. Our critical T is plus or minus 3.355. So would our T value of 3 be in the critical region if this was our critical T value?
No.
You're correct. Can you explain how what is the justification?
Because 3 is less than 3.355, therefore it doesn't fall into the shaded region.
Exactly. That's T. Maybe we should actually draw this. Let's go back to the this thing. Is this still here? Good. So let's see. So here's our distribution again, a new distribution. Our critical boundaries are going to be minus 3.355 5, 5, and positive 3.35, 5. And our calculated t that we for this example is 3. The middle of the distribution would be a t equals 0. And so you notice that 3 is not in the critical region. Remember, the critical region is the shaded part in the tails. And if we move the tails further away, if we move the critical regions further into the tails, as you would do when alpha equals 1%, that means that these critical boundaries have moved further into the tails. And in that situation, a t equals 3 would not fall into the critical region. So we would accept the null hypothesis if we had an alpha equals 0.01, alpha equals 1%. So let's go back. So that was assuming the example that we just did for alpha equals 0.05, alpha equals 0.01. That would assume that we were doing a two-tailed test, which I'll just tell you in actual practice. And I've read many, many papers that have used t-tests, and two-tailed tests are way more common in psychology than one-tailed tests. It's very, very, very rare. I'd say like 1 in maybe 250 papers that I've read uses a one-tailed test instead of a two-tailed test. But just even because the one-tailed test is a thing, we will do some examples. So once again, the example that I did right here with the babies looking at the attractive and unattractive face, we were assuming that that was a two-tailed test. Actually, I'll do these examples next time. We'll start out next class. We will do some one-tailed test examples of t-test using the same example of the infants looking at the attractive and unattractive face. We'll do the same hypothesis test, but we will do a one-tailed version of it next time. So we'll call it a day there. So if anyone has anything they want to talk about, feel free to stick around. We can chat. Otherwise, send me an email and you are excused for the day.
I have a quick question.
Yeah, let me actually stop the recording right here.
Okay.
And then I will